All right, so we're going to go over the 9496 reading guide very quickly. And all I want to do is look at the end of it, the part that deals with the essential knowledges and the learning objectives. So if you go to, that's number 16, starting with number 16 on the reading guide. It says read essential knowledge 2.C.4.G. But basically, hybridization is kind of an interesting thing because it's, there's a lot of controversy surrounding hybridization right now. Should it even be taught at all? Who knows? Where AP kind of landed on this is, well, we'll teach SP, SP2, and SP3, but we won't teach the D because there's a lot of agreement in the chemistry community right now that there are no, sorry, I'm really getting nervous about those cupcakes because I thought you were going to stick your elbow right in them. Sorry, hang on. Hi. I'm recording a video right now. You need something? Oh, okay, he needs his charger. Oh, whew. That was nice. All right, so that's going to be on the video. So basically, the idea of hybridization, you just need to know SP, SP2, SP3. And this is so easy as far as what you actually have to do with this. You just need to know if there's something with a bond angle of 180 degrees, that corresponds to something that's a linear, right? That's going to have an SP hybridization. Okay, in other words, if there are two bonding domains around the central atom, that's SP hybridization. Okay? If you have three electron domains around the central atom, you're going to have 120 degree angles. That's SP2. All right? If you have 109, really 109.5 technically, then that's tetrahedral. That's four domains, electron domains around the central atom. That's going to be SP3. All right? That's basically what you need to know. And I kind of summarized that on your reading guide as well. All right? So that's pretty simple stuff. You need to know how the sigma and pi thing works as well. But remember, with sigma and pi, that's really simple too, because you just have to remember that a single bond is always a sigma bond, right? Because the first bond that always forms between two atoms is a sigma. And then if you have any additional bonds, those will be pi bonds, right? So if you have a double bond, you have one sigma, one pi. If you have a triple bond, you have one sigma and two pi. And that's all you really have to worry about, okay? So what you actually have to do with this is not that hard. Now, what I wanted to talk about at the end of this is some application of these concepts, because they do talk a little bit here about the idea of resonance, okay? So they give an example like benzene. Atomic p orbitals overlap strongly with more than one other p orbital. Extended pi bonding exists, which is delocalized across more than two nuclei. Okay. Now I showed some pictures on this and explained it in the preview from 9496. So you might want to go take a look at that if you want to see the actual pictures here. Okay. But the interesting thing they say at the end of this that I didn't really touch on yesterday, a useful example of delocalized pi bonding is molecular solids that conduct electricity. Okay. And it says before the 1970s, it was really believed that molecular solids didn't conduct electricity. And then they started to find some things that did. Okay? So what I did on your, I thought this was important enough that maybe we could talk about it for just a minute because there's some interesting applications here. On number 17, I gave you some examples on your reading guide of things that are molecular solids that actually do conduct electricity. Graphite is one of those. Your pencil lead conducts electricity. Okay, I don't know if you knew that or not, but it does. Okay, it's actually a pretty good conductor. So it shows the structure here of graphite. Okay, now the graphite is basically, and we're going to talk more about this when we get to molecular solids in the next unit. But the basic structure of graphite, you can see these carbons are covalently bonded to one another in these rings. Okay. And you have layers that are like that. And then in between the layers, they're held together by intermolecular forces, which we're going to talk about a little bit more very soon. But that's the idea. So you take one of those layers. If you can isolate one of those layers by itself, then that's called graphene. Okay. Now I gave you a more up-close view of the graphene on the back page. No, I guess it's not yeah, it is the back page. The very beginning of the back page. Now what do you notice about the graphene structure? There's resonance, right? Okay, because you've got some areas that are double bonded and some areas that are not on the ring, okay? Because there's resonance, that means there's delocalized electrons. That means the electrons can kind of move around, okay, like they do in a metallic solid. So these things will actually conduct electricity, okay? And then you've got the carbon nanotubes, which is basically just you take a graphene sheet and you roll it up, and then you've got a carbon nanotube, okay? So there's some really interesting applications of some of these. What I did is I got online just for fun here, and what I found were the scholarly websites on potential uses for graphene and the potential uses for carbon nanotubes, and then I found just the tech websites, and those were a little bit more fun. So I'm going to show you those if you don't mind. But I double-checked some of this stuff to make sure it was really correct. Yes, sir. Okay, it would take an elephant standing on a pencil to break through a sheet of graphene, okay? So obviously one of its best qualities is its amazing strength, okay? So with the graphene, here's some potential uses for it, okay? It's a good conductor of electricity, a lot lower resistance than some of the silicon-based stuff that we use now for computer chips. So mega fast uploads is a potential use for graphene, all right? Now, some of this stuff is a ways away, okay? But you should see some of this happening in your lifetime. Plug in the phone for 5 seconds, it will be all charged up. It's kind of nice, right? Okay, because you can get a lot of current through there without so much resistance, because it's not only is it heat resistant, but it just doesn't produce as much heat as a typical electric current running through the copper wires that we use now. This one's interesting. I didn't find this one anywhere else, but I mean, I think it's probably true. I don't know much about Gizmodo, so hopefully I'm telling you correct information right now. But it could potentially clump together radioactive waste, and I'm not exactly sure how that would occur. But that was kind of the random one that was thrown in there. Could improve your tennis game, putting the weight where it's more useful in the head and in the grip. Really, with a lot of design type, engineering type stuff, you can build these things kind of from the ground up, because you're building one sheet at a time. All right, so you can decide how much of it you want to put into a structure, where you want to put it, and it can make things a lot stronger and heavier where they need to be and lighter where they need to be. Okay, this is interesting. Because again, we're working on the nano scale here. We can make a filter with holes that are just the right size, okay? Sodium chloride's a little bit bigger than a water molecule, right? You can look at the molar mass on the periodic table and you can tell that. So we should theoretically be able to make a hole that's big enough for water to squeeze through, but small enough that salt can't, okay? So you basically have an instant filter for salt water, which I thought was pretty interesting. Touch screens that use graphene, no more broken phones ever, okay? Unless you have an elephant standing on the head of a pencil. Single sheet of graphene can produce headphones that have a high frequency response comparable to a pair of Sennheisers, which I don't know if you're an audio nerd, maybe you know something about that. I don't really know. I'm not familiar with that brand, but evidently it's pretty good. High-power graphene supercapacitors could make batteries obsolete, so this could be the new way that we power all of our electronic devices. And possibly bionic devices, okay? I thought this was cool too. Could be connected directly to your neurons, so people with spinal injuries could relearn how to use their limbs. So a lot of really, really cool application with this. Just for the sake of time, I won't show you all the nanotube ones because they're really very similar, because again, nanotube is just graphene rolled up into a tube. Okay. But you can use those nanotubes. One of the things that maybe, yeah, I don't know what people's obsession is with those space elevators. I mean, I just feel like that's not a good idea, but maybe it is. I don't know. Okay, so the idea is, hey, let's not spend so much money on rockets up into space. Let's build a space elevator that runs on a cable made out of carbon nanotubes. And the cable would be strong enough, you could like string it from here to the moon or something, and then just take a space elevator to the moon. Or, yeah. Okay, and that's well, the nanotubes are a little bit harder to make. The graphene is surprisingly easy. That's one of the great things about graphene is that it's not difficult to make it. I read in one of these more technical articles that some researchers are making it using a CD burner. So, and I'm not sure exactly how they're doing it, but because it didn't go into the details of how they were doing it, but it said that it's just very easy to make. So that's one of the big advantages of it. Another big advantage is carbon is very readily available, right? I mean, it's everywhere. So it's just, it's interesting all these different applications that you have for it and some of the potential uses. So I wanted, every once in a while I like to kind of stop and just talk about how this stuff can actually be used in real life. Every once in a while it does have real life applications. Actually, a lot of times it does. Yeah, so you don't feel like it's just a total waste of your time. This class is not a waste of your time, I promise. There's a lot of good stuff here that you can use later. The last question here, the challenge question, figures 928 and 929 in the book discuss the delocalization of electrons in a benzene ring. So the question is, why doesn't benzene conduct electricity, but graphite does? And that's actually kind of a tricky question because benzene really does have that delocalized electron structure, just like graphene does, okay? But if you compare the graphene picture that I have here to the benzene picture, benzene is just one isolated ring, okay? And that's the difference. They are delocalized electrons within that ring, but each of the rings is isolated from one another in benzene. They're only connected by intermolecular forces. If you look at the graphene here, all of these rings are interconnected to one another, and you can just have this network of rings. So the electrons are free to kind of travel throughout the rings, all right? So that's the difference. I guess benzene technically could conduct electricity within one ring, but that doesn't really do you any good because we're talking on the miniature arc reactor. I don't know what that means, but
You haven't seen Iron Man?
I've seen Iron Man.
Yeah, the thing goes around in circles of light.
Oh, okay. So you're just referring to the one benzene ring as a miniature arc reactor. Okay. All right. So anyway, there's some potential applications, and I think that's kind of what they were hinting at when they went over that in the essential knowledge stuff. So yeah, we'll end the video with that, but I thought that was kind of interesting stuff.